Hello everyone and welcome into yet another live stream. Yes, it is the time again, the time for physics. Just like that time, but this time it will be better because with me it is the one, the only quantized eigenvalue of physics. It's Remko.
Thank you very much, MAKiNG. We are here for a lovely time. How's it going with you?
It's going well. It's going really, really well. And how's it going with everyone right here watching right now? How are you all doing? How are you all doing?
Look, this is the messages I want in chat.
Let's see. Okay. So, hi there, Bayern. I see. Hi there, Zima. Hi there, Mashrit. Hi there, everyone. Hi and welcome. Hi and welcome. How are you all doing on this fine day? I hope this time everyone can hear you as well. Backwards going clock. Someone, Mashrit noticed instantly. I genuinely thought no one would notice it the entire time. Impressive.
That is very impressive.
Yeah,
Let's see if they find more details.
Yeah, there isn't much yet. Well then, I suppose enough of the preparations, you will know the deal by now. This is the live stream before the video. And that's because in the video there's going to be more visualizations, but on a live stream there is something different. And that's you, because you can ask questions. This will be the proper explanation, and in this explanation some things may be confusing, so do feel free to ask questions. Genuinely, do not be shy. It's fine, that is quite what we're here for. And with that in mind, I do believe we should start the recap. What do you think?
Yes, welcome back everyone to the second edition of Chasing the Equations of the Universe. So let's quickly do a summary on what we did last time. The board is up.
The board is in fact up.
Perfect. So we started last time with thinking of Newtonian mechanics, where we described a system in terms of x and v, position and velocity. For example, the free particle. And we could determine the behavior of the particle entirely by its position and velocity using forces and such. But then we shifted our point of view and instead considered energy as our perspective of the system. And for this, we defined the Lagrangian, which for most systems is just the kinetic energy minus the potential energy. For the purposes of this stream, I will be writing the v as which is the derivative of x. I'm going to write that as x with a small dot on it. If you're ever confused about this, just ask.
Yes.
Any time derivative will be a dot.
I do believe we mentioned that in the last video. That's because in this case, what is important to keep in mind is that these are generalized coordinates, which means it doesn't really matter for most purposes. You can think of it as just position and velocity. It's completely fine. As standard linear position and velocity, but it's useful to keep in mind as generalized coordinates because this entire theory is extremely general. So this was once again, or this is just a review covered all in the last live stream and video. Is there going to be Lagrangian mechanics? Quite the contrary. You shall see.
You shall see indeed. So the problem with this function was that it had way too much information. It had every possible combination of kinetic and potential energy, and therefore we did a small trick to find only physical solutions. And we did this by calculating an integral from which we got the Euler-Lagrange equations. This is an equation which, when you have a Lagrangian, you can solve this to find the equations of motion, so the behavior of your particle. And what we saw, we did some examples, what we saw about this equation is that it gives us exactly the equations that coincide with the Newtonian formalism of the forces. So that is what we did last time. But in the last stream, there were a couple questions on using the velocity, the time derivative of the position, as independent coordinate, because naively it would seem they are very connected. They are not independent because you're taking a coordinate, you're taking a derivative of a coordinate. Well, technically they are sort of independent, but we are going to justify this in a bit more detail. So what we're going to do now is we are going to define a whole new variable, which is definitely going to be independent from position. And
I'd really have to say that we did already have some predictions here because, well, as for coincidence, Bionerd just asked, what is momentum, Remco? And then the typical response from Sissy, which is momentum is mass times velocity, and then from Mashrit, no, momentum is the partial derivative of Lagrangian with respect to velocity. So, even though we haven't spilled the beans exactly, we already have some on-point comments.
We have some. Yes. Also, can you check the stream real quick? I don't think it's showing the equations, or you scroll down.
Yeah, I scroll down because, yes.
Perfect. Yes, so what we're going to do is we are going to define a new parameter, namely the canonical momentum. And we will see in a second why we do this and why we call it the momentum. We are going to define this canonical momentum, as rightly observed in chat, as the partial derivative of the Lagrangian with respect to the velocity. So, first of all, immediate question. Why do we define this and why do we call it the momentum? Well, that is easy to see, actually, because what we can consider is, let's just say we have a Lagrangian, which we know is the kinetic energy minus a potential energy, and we are going to let this potential not depend on velocity or time. What will happen? We can like calculate the canonical momentum for this, which is the derivative of the Lagrangian with respect to the velocity, which in this case is just mx. So when we are considering a potential that does not depend on velocity, we recover the equation for momentum that everybody knows. And so this canonical momentum is a generalization of our usual momentum.
Yeah, so in this case, there is the mathematical reasoning to show that it is actually equal. There is no foolery going along. But at the same time, we can kind of interpret what it means just from the equation on its own. So mathematics is obviously the most important. But at the same time, we can pause here and ask for a second the question of what does the partial derivative of the Lagrangian in relation to velocity even mean? Well, as we remember, the Lagrangian would be the kinetic energy minus the potential. The potential on its own we will ignore for a second because, well, that is a bit complicated. So let's just focus on the fact that in this case, the Lagrangian would be proportional to the kinetic energy. So the reason why I'm focusing on this is because what this effectively would state is that this is kind of like our derivative of how the kinetic energy is changing in relation to the velocity. So you can think of as kind of efficiency of energy with increase in velocity. If you have a really massive cube, you can increase its velocity a little and increase the total energy a lot. So that's kind of how momentum operates in this case, which is why it's a neat definition of it. Yeah.
The potential that depends on x can be a non-constant, but it could technically also be a constant. It just wouldn't do anything. The main thing is the potential does not depend on velocity or time. Well, specifically velocity. Okay, so now we have two variables. Position again, and the canonical momentum, which I'm just going to call the momentum from now on. So momentum is always canonical in this sense that it is a derivative with respect to of the Lagrangian with respect to velocity. These two variables seem a lot more independent than position and velocity. So we're going to work with them from now on. And we are going we are now going to introduce the Hamiltonian formalism, which I mentioned last time in the stream. So what we want is we want a function that only depends on these two variables and not on velocity anymore. I will just give the definition of the Hamiltonian, and then we will see in a second why this works. So the Hamiltonian, as function of position and momentum, is defined as the momentum times the velocity minus the Lagrangian, which is the function of position and velocity. I am from now on going to write the variable dependencies of the functions for the Hamiltonian and the Lagrangian, just so it is clearer. So you immediately see, oh, this is a function of x and p, this is a function of x and velocity. All right. For now, let's just go with the flow. What does this give us? Let's see how it behaves when we slightly vary x and p. So what I mean with if we slightly vary x, this is usually done by a derivative. We're going to see how the Hamiltonian changes when we slightly vary it with respect to x. And we can immediately see that this first term does not depend on x. So only the second term depends on x. So what we get is the minus sign, the partial derivative of the Lagrangian with respect to x. Now, let's do the same for the p. And in this case, we see that the Lagrangian does not depend on p, but the first term does explicitly. And when we differentiate with respect to p, we only are left with the x dot. So the second equation is nice. The first equation still requires some work. Well, in this case, what we know is that we have the Euler-Lagrange equations, which I just mentioned in the summary, which need to hold for physical solutions. We can fill those in. And what we get is minus the derivative with respect to time of the Lagrangian, the derivative of the Lagrangian with respect to velocity. But this is exactly what we defined as our canonical momentum. So instead, we end up with a time derivative of momentum, which is just p dot. So here we used the Lagrangian constraints to the Euler-Lagrange equation to get a constraint for the Hamiltonian. These two equations, the derivative of the Hamiltonian with respect to p is the velocity of x, and the derivative of the Hamiltonian with respect to x equals minus the momentum, are called the Hamilton equations. Let me mark them with red, because these are the counterparts to the Euler-Lagrange equations. They are of the same importance. So let's step back on why we wanted to do this before going into some examples to make this all a lot more clearer. So first of all, we now have a function, the Hamiltonian, that only depends on position and velocity. And this position and momentum, canonical momentum. And this is a much more natural notion of than velocity. And a second thing is, when we were solving the Euler-Lagrange equations, we had two derivatives. We had a second order differential equation. We had a derivative with respect to velocity, but followed by a derivative with respect to time. But now we have two equations which are both first order differential equation. So this is usually a lot easier to solve. But what is the cost of doing all this? Well, from the Lagrangian equation, from the Lagrangian, we knew what it was. We knew it was the difference between kinetic and potential energy. It had a very easy interpretation. But what do we know about the Hamiltonian? That is still something we need to investigate, and we're going to do that with the two examples. In the meantime, let me ask you, Make It, if there are some questions in chat, because I cannot see chat.
I do believe that there aren't so far. Everyone seems to be understanding it perfectly clearly. We did have two backup segments planned, and I don't think we need to go into either of them so far, because so far everyone seems to be ahead of schedule, if anything. I'm just sitting here silently, absolutely not adding anything, because so far I think we're safe.
That's all right. So we now have the Hamiltonian, and we are going to get two examples on what we can do with this Hamiltonian, what it means. First example is, of course, the well, you can have a guess.
The one and only, the one with the graph that we all adore and love.
It is, in fact, the free particle. Let's just calculate the Hamiltonian for the free particle in...
Maybe as a comparison
with
first,
what
we could do also the Lagrangian. As
yeah,
we could note down from the previous video just as a comparison.
Yes. We knew that the free particle had no forces acting on it, so the potential energy is 0. So we only have to deal with kinetic energy, which is exactly a half mv squared, or x dot squared. So first step what we do is we start calculating the canonical momentum. Well, we know its definition. We can easily calculate this, and in fact we have already done this. Because this is just the normal momentum. Now, from this line, from this, we can calculate the Hamiltonian, since we now know P. And this is equal to P times x dot minus the Lagrangian. This is by definition. And we can just fill in the Lagrangian, which was minus a half mx dot squared. Now, we already run into our first problem, because our Hamiltonian needs to be a function of x and p, position and momentum. But right now we have a function of p and x dot. So we need to get rid of this x dot factor. We need to get rid of the velocity. But fortunately, we just calculated the canonical momentum, and what we see is that we can divide both sides with mass to get this equation. So what we're going to do is, in this Hamiltonian, we substitute all the velocities with p over m, and we should find a equation that is just a function of momentum. So let's do that. First we have p over m, and then we do the same thing. In this case, it's squared. And what we find is p squared over m minus a half p squared over m. The m's cancel. So this is equal to a half p over m. And this looks almost the same as the Lagrangian. And this is also the reason why I went so effortlessly between velocity and momentum in the last stream. Because in the case of the free particle, nothing significantly nothing like of importance happens. It's just very straightforward. You just use normal definition of momentum, mv. You just substitute it in, and you get your a half p squared over m. But we can now solve this. We can now find the Hamilton equations. The first one was the time derivative of momentum is minus the Hamiltonian with respect to x. And we already see this is 0. The Hamiltonian does not depend on x. We can already see that means momentum is constant. So it does not depend on time. The second one is x dot, and this is equal to the Hamiltonian with respect to p. And here we see that we can just cancel the factor a half with the 2 from the momentum. And what we now know is this momentum is a constant. We just saw that it's constant. So that makes it very easy to integrate. So we do find the exact same expression as we did with the Newtonian and the Lagrangian case. So once again, we found that it coincides with Newtonian and Lagrangian. That's very good. Let's make it a bit more difficult. Let's add the harmonic oscillator. Let's consider the harmonic oscillator. Do you guys still remember the Lagrangian for the harmonic oscillator? Who knows? Who remembers? This is quiz bonus points. Of course, we start with kinetic energy. But what was the potential term? Make it, perhaps you remember.
Oh, me? Oh, I haven't got the slightest clue. I imagine it will be very different from the kinetic. I don't think anyone either remembers or, to be honest, frankly, Ren is close. Ren is close.
Yes, Ren, in your case, you have the force. We want to consider the energy.
Yes,
and the energy is indeed
there we go.
a half kx squared. Yes.
Oh no, it's a
good job. You all get passing grades.
Don't worry, Ren. It is a fairly common mistake. In this case, this was very much close enough because from the force you would relatively easily get the energy.
So let's calculate the canonical momentum again. And very fortunately, it's exactly the same derivation because our potential only depends on x. So once again, we get m x dot. So we immediately write this as velocity equals momentum divided by m. Now we can calculate the Hamiltonian again of function x and p. And this is p x dot minus Lagrangian. Sure, this is p x dot minus a half m x dot squared plus a half kx squared. And once you substitute all the velocity in for momentum over m, you end up with p squared over 2m plus kx squared over 2. And notice the difference between the Hamiltonian and the Lagrangian. The only thing that has effectively changed is that the minus became a plus. So what we see here is that where the Lagrangian is the difference between kinetic and potential energy, the Hamiltonian is the sum of them. The Hamiltonian is a function for the total energy. So when going from Lagrangian formalism to Hamiltonian formalism, we did not lose any information. All the information is still there. That is good. That is exactly what we want. So once again, let's solve Hamiltonian equations just to get more comfortable with the formalism. First of all, the Hamiltonian with respect to x is now not a constant. It depends on x. And the time derivative of x is the derivative of the Hamiltonian with respect to p, which is once again p over m. So 2 things to note here. Now, the problem now is that x depends on t and p depends on t, so on time. So we cannot easily integrate this anymore. So this is a coupled system of differential equations, and it requires a bit more work to solve them. But in this case, it's still slightly easy because what we can do is we can get the Lagrangian equations back. What we can do is we can differentiate the second equation with respect to time. So we now have two dots. This means the second derivative with respect to time. And this is going to be the derivative of p divided by m. And we know what the derivative of p is by the first equation. It is minus k t over m in this case. So what we see once again is two derivatives and you get a minus sign. So this solution is a sine or a cosine or an exponential in general. This is good because this is exactly what we saw in the Lagrangian and Newtonian formalism once again. So that was just two examples to get. Yeah.
Yes, is everyone clear on all the happenings so far? I just wanted to set it because so far it isn't much. So far it is just the examples that we have gone over twice. This is the third time. So far we've gone over this with Newtonian, Lagrangian, and now Hamiltonian. So is everyone clear on what just happened? In the meantime, you can set up the next example, I suppose, because we could count as a third example, I believe. Complex thing keeps asking, are these product scalar or product of magnitude? I don't exactly know what they're referring to.
I do not see the messages in chat.
Are these product scalar or product of magnitude? That is the question. The entire question. Which is why I'm a bit confused. Also, Said, I'm glad you loved Lashim. To go on.
Could you explain the question, complex thing, please?
Yeah.
In the meantime, I will raise a point because what we have done now is we have found that the Hamiltonian formalism is equivalent to Newtonian and Lagrangian, at least for these examples, but in more general, they are equivalent. So why did we introduce another formalism? Well, this is a massive spoiler for what's going to happen later in the live stream. But it turns out that the Hamiltonian formalism has the perfect tools to make the jump from classical to quantum mechanics. Well, then you might ask, why didn't we go immediately to the Hamiltonian formalism instead of first going to Lagrangian formalism? Well, when we go to quantum field theory again, we need the Lagrangian. So, and also a second reason is that the definition of the Hamiltonian in terms of the Lagrangian is much easier than just going straight to the Hamiltonian. So even though these two formalisms are so, well, they are related easily, it turns out that the Hamiltonian is necessary for quantum mechanics and the Lagrangian formalism is necessary for general relativity or quantum field theory. So let's get working on this jump to quantum. In this case, P product X dot is just normal scalar product. It's just, they are both functions of time, which means they are both a single-valued number, or they are being mapped to a single-valued number, so it's just the multiplication of two numbers.
Yes.
But yes, let's make things slightly more complicated. Because there is another reason why we prefer Lagrangian and Hamiltonian formalism over Newtonian formalism. And that is that they are very easy to extend to many particles. So what we're going to do now is we're going to consider a many particle system. And so let's say we have a total of n particles. Let's not give it a number. Let's just immediately go for something abstract. If there's any questions in chat, just ask. I can make it more easy. Let's say we have n particles, and you could fill in any number you want for n. positive integer, please. And what we do is, let's say particle 1 has position 1 and velocity also 1. And similarly, particle 2 has position 2 and velocity 2. And in general, particle I, where I is an index, has position I and velocity I. So these i's are just abstract notation for an arbitrary particle.
Index of each particle.
And here, of course, yeah, and here I runs from 1 to n because we have n particles. What we then could do is the Lagrangian is kinetic energy minus potential energy. We know that much. But you can add energies together, which means that we can, like, for example, add the kinetic energy of multiple particles. So what we get if we want to write the Lagrangian of our entire system, this is now a function of not only one position, but it's a function of n positions from each particle 1, and similarly for the velocity. And this is just going to be the kinetic energy of the first particle plus kinetic energy of the second particle plus etc. Now, Lagrangian is also, we also need to subtract the potential energy. So let's do that. Let's assume that the potential only depends on potential energy only depends on position. So we'll just add the potential energy of the first particle, the second particle, etc. So it's just a whole. It's a very long equation, which basically doesn't tell us that much information other than just add all the potential or the kinetic energies and subtract all the potential energies. Now, there is a very nice shorthand notation for writing this, which is using the symbol. So this sigma symbol just means that we add this term, the kinetic minus potential. We just do this for every single particle. So that means the Lagrangian is also additive. If you have a Lagrangian of 1 particle and a Lagrangian of 2 particles, we can just add them together and we have our whole new Lagrangian. And as a massive spoiler alert, this is exactly why we love Lagrangians, because especially in quantum field theory, because if we have, for example, the Lagrangian for electromagnetism, just say, we randomly have that one, we could just add the Lagrangian of the weak force. And according to this, everything would just work out. We would have a theory of electromagnetism and the weak force together. So I think everyone has seen that like huge ass equation of the Lagrangian of like the entire universe. The one that you put on shirts, but then the shirt is too small. This is not just a hoax made up by the physicists to seem cool. This is actually how Lagrangians work. You just keep adding terms and you keep adding interactions just by summing them. And in this case, the Lagrangian equations, or the Euler-Lagrange equations, you now have a total of n of them. So you have one Euler-Lagrange equations for every single particle. Now, this follows from doing the integral equation, what I did last time on stream, but then n times, basically.
Yeah, summing them together. So is the sum of the Lagrangian? Yes, it is the sum of the Lagrangians, effectively. Because that's
I could.
Yeah, that is what we're doing in this case. We're just we have an n amount of particles, so we're just adding all the n Lagrangians. In this case, it is maybe fairly not visible in the top notation, but it is effectively just this sum right here.
The nice thing is that because the Lagrangian is additive in energy, this means that once we consider the Hamiltonian of the OD particles, which now is defined as this, so you sum over the product of canonical momentum with velocity of the particles minus your Lagrangian, but your Lagrangian is now a huge sum of tinier Lagrangians. So what will happen when you work this out? You will see that once again your Lagrangian is also additive. So you also have your Lagrange. I'm sorry, keep saying Lagrangian. I mean Hamiltonian. Your Hamiltonian is also just a sum of smaller Hamiltonians. You can add Hamiltonians together to get a new one.
Well, I suppose in this case it doesn't matter. They're both additive, the point is. So they're both Lagrangian and Hamiltonian.
Yes. And once again, you get like the Hamilton equations for each particle. Now, before the things get real, let's consider one more thing. Let's see how the Hamiltonian changes in time. For this, let's just consider a Hamiltonian that does not explicitly depend on time. So we only deal with a function that is we deal with the Hamiltonian as a function of position and canonical momentum, and not of time. Because we could actually add the time here. I probably should have mentioned that before. Your Lagrangian can explicitly depend on time. But these cases are very rare and don't really happen in the universe as far as I'm aware. So we usually just don't consider explicit time dependence. The thing is, when we want to consider the change with time, is that our Hamiltonian depends on position and momentum, but both of those depend on time. So when we want to slightly change time and see how our Hamiltonian reacts, what we need to do is we first slightly change time explicitly. Well, we already knew this is going to be 0 because our Hamiltonian doesn't depend on time. But we also should look with how our position slightly changes with time, because this term will contribute, and the same holds for momentum. Is this clear? Because this is a very important step I'm making here.
Yes. So here's the question: how many people here are familiar with the chain rule? Because I do believe it will be quite a few, I imagine, considering how so far everyone chatting here seems to be, I would say, more than overqualified. Good for all of you. But if there is any confusion about how did this come to be, how did we just take a derivative in relation to time, only to then end up with effectively 3 different derivatives, or a sum of the 3 different derivatives. And also all of them being partial, very important to mention. The reason why we have d on one side, partial on the other. Is this something anyone needs an explanation of? If so, say now. I am happy to provide it. I've been sitting silent the entire stream because, well, Remko is doing a banger job. I don't need to intrude in any way. So...
yeah, speak up now or forever hold your peace, I suppose.
I thought for the
Alright, make it, go explain it.
I thought for these derivatives we keep all other variables constant, so I don't really get it. Okay.
Yes.
I see. So basically, in this case, what's important to realize is that this is the Hamiltonian. This is a function of 2 separate functions on the inside. And the reason why we are taking these partial derivatives instead of normal derivatives is effectively because we want to note it down in a way that gives us some more information. So, let's give you a very, thank you so much for dividing, let's give you a very standard make it example, just off the top of my head, something that we can all relate to. Let's say that you have an object, that object being a cube. Remko, we're gonna control Z now, it's gonna be problematic. There we go, beautiful. Mwah. Let's say that you have an object. That object being a cube, we're all familiar with cubes. We all have them and use them in our day-to-day life. Now let's say that we are in this very relatable scenario where we need to set it on fire. Setting it on fire will do something. This is my rendition of what a fire looks like, a fireball to be more exact. And let's say that we would like to set our cube on fire to achieve some kind of effect. Now, the rules are simple. The hotter the fire, the quicker our reaction of a cube will happen. You can think of it as a chemical reaction, as a physical process, doesn't matter. Something happens to the cube, and the hotter the fire, the better it is. Now, for this fire, we would like to use some kind of fuel. This fuel are represented with pellets. I don't know what they are. They could be coal. They could be something else. Frozen ethanol, doesn't matter. They could be something that I cannot even mention on this live stream. That is our some kind of fuel. Now, if we change up our fuel, this will in fact impact what happens to our cube. But there is a degree of separation there, because our change in fuel won't impact the cube directly. Instead, the change of fuel will change the fire, which in turn will change the cube. And so far all I'm talking about is a bit abstract, so let me make this more concrete. Let's say that we have some kind of unit of energy for a fire. The exact unit doesn't matter, something arbitrary, and right now it is at a 5. Now let's say that this unit determines how quickly, or maybe how grand our reaction of the cube is. So maybe how many kilograms of the cube material we can process. So let's say for now it will be 10. So for each 1 unit of fire energy, we can process double that amount of the cube. Now, let's say that we have another unit for our fuel, and this fuel determines how hot the fire is. So let's say for now it would be something like 1. Okay, now if we change our fuel up to be more potent, so for example to bring it up to something like a 2, then our fire will be twice as hot. So it would be a 10. But if it's twice as hot, that means we can process twice as much material of the cube, which would be 20. So in this case, our change in fuel changes our reaction on the cube. I do believe this is all intuitive and simple, but what is crucial and important to remember here is that this fire doesn't have to act on the cube in a linear fashion. It can act on it in a different fashion. And one really nice way to model it would be to realize that our fuel, we can think of it as a variable, x. The fire would be the function applied on x, and the cube will be the function, let's represent with g this time, but the function of what? Well, that would be the function of our fire of x. So in this case, the small difference in x will result in a different distance in f, which will result in a different difference in g. And so in this case, this is effectively what we did right here with the partial derivatives. Because in order to determine how our change in fuel will affect our cube, we need to take the change from our fuel to fire and multiply it by our change from fire to cube. So in this case, what we are doing is, if we want to determine how our Hamiltonian will change in relation to position, we need to figure out how the Hamiltonian, well, or rather, because the position to time, right? So how our Hamiltonian will change with respect to time, then we need to figure out how our Hamiltonian will change with respect to position, and how the position will change in respect to time. We multiply them both together, because that's the degree of separation. And then we obviously add together also the change in the Hamiltonian in relation to momentum. You can't see me, but I'm doing air quotes. And momentum in relation to time. And on the very beginning, we obviously add the t itself. If it was there, then we would obviously have it as being dependent on its own. I'm glad that KM just said, oh, that makes sense, because that means my explanation was useful, at least in some way. And well, unfortunately, we cannot show you it with an experiment in real life. I tried, I lost all the material. It's a long story, doesn't matter. Back to you, Remko. Because we have this equation, but what does it even mean?
Yes. Okay. So MAKiNG just nicely explained the chain rule there. One thing I quickly want to add is that the difference. I saw a message in chat asking about the difference between total or normal derivatives and partial derivatives. This was explained in the last stream, but I can quickly mention it here as well. In case of a total derivative or a normal derivative, you just check how your function changes with respect of time. Regarding every single variable, just doesn't matter what changes with respect of time, you just look if something changes with respect of time. In case of a partial derivative, you hold everything else constant and you only vary this one thing with respect to time. So you only check one specific variable to change with time. Okay, so when we want to check how the Hamiltonian changes in time, we want to check all these three components. But I started this whole talk with Hamiltonian doesn't explicitly depend on time. So what that means is this term is zero because this checks if the Hamiltonian is explicitly dependent on time. That's nice. Now, this term is of course just x dot. That's also good. We know this. What we now can do is, hey Ash, what we now can do is we can check the Hamilton equations again, because they are hiding something from us. Maybe you could show the both the Hamilton equations and this equation, please.
Oh, that's gonna be difficult.
Is that possible?
That's gonna be difficult.
It might be small, yeah.
Yeah, but the point
All
is,
right, let's just
partial in relation to p equals x dot, partial in relation to x minus p dot. There's a bit of a pattern there, so this, and then with that in mind.
Okay. Yeah, with that in mind, we notice that same symbol here, the partial derivative of Hamiltonian with respect to x. This is minus p dot, and we still have the x dot. But what we also see is partial of the Hamiltonian with respect to canonical momentum. This is your x dot, and we still have the p dot. Now, this is zero. What does this mean? This means that your Hamiltonian is a constant with respect to time. It doesn't change with respect to time. And why is this good? Well, we said that the Hamiltonian was the total energy. So what we just showed here is energy conservation. I think that's pretty neat.
I think so as well. Very, very muted reaction, but yes.
Yeah, the response to this is so underwhelming, even though it should be so overwhelming.
Just showing that.
This is a huge accomplishment. We just showed that energy is conserved, and then it's like, oh, yeah, happened. I guess so. All right. Yes, thank you, Ren. This is the response I wanted. So let's use this a bit more, actually. Let's just generalize this whole chain rule derivative. So let's say we have a function that depends on position, canonical momentum, and time. We're going to slightly vary it with respect of time. What this means is it just means what we did just now with the Hamiltonian, but now we just consider an arbitrary function. So we have the same equation. First of all, we vary it with respect of time partially. Then we vary it with respect to position, and we vary position with respect to time. And same for momentum. And what we're going to do, well, if we have n particles, so if our function, what I'm going to do is I'm going to give this derivation for one particle, but I'm also going to give it for n particles if you want it to be slightly more advanced. And I also need this for later purposes. So in this case, your function is, your f is a function of all the positions, all the momenta, and time. And in that case, what you get is the same thing, except now you need to do this for every single particle. So I'm going to immediately write the sum here. So we are going to check how it changes with respect to position. Of course, also varying position with respect to time. And the same for momentum. But we need to do this for every single particle.
Yeah.
It is the same essence, it's just
equation, except this time
more
we
general.
have the I. We have the index ones because there are multiple. But if I display them side to side, it's... Yeah.
Yes. So back to the first one. What we are going to do now is we know how to write x dot. So if we have a system with a Hamiltonian, we're considering n particles, so we can just create a Hamiltonian. We know what x dot is because and also p dot. Those are exactly the Hamilton equations. So what we get is we can just substitute it. What we can do is we still have the derivative of f with respect to x, and x dot is going to give the derivative of the Hamiltonian with respect to momentum. And the same for p dot, but now we get a minus sign. And let's immediately do the same on the other side. So it's the same step, but we just do it once again for every single particle. Let's hope I don't run out of space here. If I'm writing too small or something, please do tell me and I will try to write bigger.
Good. On this side, I also have to say there seems to still be some confusion about the partial derivatives. Well, I want to have a bit of fun with the phi explanation, but I do have to say, Ren did mention the gears explanation, which the second I saw the comment, I knew that was definitely would have been the right way to go. So if you're all still confused, then I can explain it once again, with this time with gears, which honestly I think will be much easier. But that's if there's enough confusion. For now, let's just stick on point, which is these two equations right here.
Yes. So what we're going to do here is we're going to, this is a very long expression and you get tired of writing this so many times. I already get tired from writing it twice. What we're going to do is we're going to give this term a little name. It's called the Poisson bracket, after the guy that gave this the name first. I'm going to call it the fish brackets because I don't support the French. It's written with curly brackets. That's a joke for reference sake. If there's any French people, I'm sorry. I appreciate you.
At the same time, there is another words we'd like to use on this live stream, but unfortunately, for the sake of YouTube content policies, we cannot use them.
Let's... When we consider both cases, the first case, it's easy. The Poisson bracket is literally defined as the product of these two partial derivatives minus the other two. For the other one, for the many particle case, we consider all such products. So we consider the sum of all these. And this is what we're going to just take as a definition. So when writing it using this definition, in both cases, it will look like this. First case, it will just be the partial derivative with respect to time plus the Poisson bracket. For the second one, it will be exactly the same.
Yeah, now let's... Honestly, I want to just mention what does it maybe mean? Because sometimes it's really easy to get lost in equations, but... and actually, I would like it as an exercise to all of you. By looking at this equation, by knowing that these are in fact partial derivatives, which means they just describe change of something in relation to something else, I would like you all to make a guess or describe it to the best of your ability of what this kind of Poisson brackets mean. What do they mean? What do they mean exactly in this case? We start with a function. We're basically trying to figure out how function changes over time. Functions depend on the x, the p, and the t, so the position, the momentum, and the time. And then from it we get these right here three derivatives, effectively. Generator of time evolution. That is a very... not the language I was expecting. I'm thinking if that is... I was looking for.
I think technically it is a generator of time evolution.
Not very much not the language I was expecting.
Let's just say not in the context of this stream.
I gotta say, Ren so far has been ahead the entire time. I'm not even sure how we got the some brackets. Oh, this is it. These right here are the brackets.
Yeah, it's a definition in this case.
This is the definition. If you set inequality, I'm drawing it vertically because, well, such is life, but anti-commuting of momentum and position derivative operators, maybe.
I guess the equality could be here.
Actually, the answer I was looking for was way simpler. Way orders of magnitude simpler. Just simply to not get lost in it. This is the change, this is basically describing how the function f changes in relation to time, but disregarding the explicit time. That is effectively it. That is genuinely all there is to it. It's just important to keep in mind because in the future, when you see Poisson brackets, and then when you recall the definition, you might get overwhelmed for a second because you will just see, well, effectively 8 partial derivatives, or well, 8 partial derivative symbols, which, let me tell you, triggers a fear response in all mammals that causes fight or flight instinct to kick in. And as such, it's just useful to keep conceptualized things in mind.
I am one of those mammals. So as MAKiNG said, this Poisson bracket or the fish bracket measures the change in the function that is not explicitly caused by time. So in other words, what this means is that it tells us how the function f changes when the coordinates change. Only the coordinates. Okay, so let's do some magic with these Poisson brackets, just because we can. We had an arbitrary function when we started, so now we can actually pick a function we like. And I guess one of the more interesting cases is when we just let the function only depend on x. Why is my pencil not writing?
Oh, doing too. My handwriting is terrible in capacity because I'm writing with a mouse, so I don't know if I can fill in for you all that well.
I'm gonna reload my board because it's loading.
Yes, we are in fact duplicated on the board. There is 2 of you and 2 of me.
You know what? Let's just
twice
keep
the fun.
Going.
Twice the heads, twice the fun. Doesn't matter. Everything works out. Don't you anyone worry about it. It's fine. The question is, what if we set the f of x, p, and t to be just equal to x, just position?
Yes, you can see it on stream, right? I can't see the stream right now.
We can see it on stream. It's all fine.
Okay, perfect. So yeah, we choose the function to be x because we can have a general function. We can just pick whatever function we want as long as it depends on x, p, and t. Well, we just let it depend on x. Everything that depends on p and t, we just set to 0. What we then find is we're interested in the derivative of this function, which is now just x. So this is, as we know, it's just the derivative with respect to position to time. There is no explicit dependence of in x of t. So the first term in our definition vanishes. I will just write it down just in case. This one vanishes. So what we're left with is the Poisson bracket of x and h. But this is very nice. Because we can just write this one out. I'm gonna Control C it slightly so I have more space. I appreciate the fish.
Thank you. I thought you could
go throw it a friend while I write this expression down. I'm just going to use a definition of the Poisson brackets here. And this is also one of the reasons why we use Poisson brackets. because imagine if you had to keep writing this every single time.
Yeah, humans can only stomach a certain amount of partial symbols, and 8 is definitely over that limit.
Yes. Okay, so we did it. We have now this expression, and now we can actually figure it out. First of all, the first term, the derivative of x with respect to x, this is 1, obviously. In this case, this term, the derivative of x with respect to p, is 0 because x is independent of p. And definitely doesn't explicitly depend on p. That would be weird. So what we are left with is this. And if you read now the full line, x dot equals a derivative of h with respect to p with respect to momentum, this is exactly Hamilton's equation. What this means is we could express Hamilton's equation in terms of these Poisson brackets. We could write this, and it has exactly the same information. And now we could do the same when we consider a function that only depends on p, or that is p basically. Then, well, make it rules on other fish. I can write down this whole expression.
Don't make me draw any more fish. That's enough.
But there's so many Poissons
Which
here.
part of physics did we play last time and now? Last time it was Lagrange mechanics. This time it is... Oh, dare I spoil? I don't think I dare. Let's just say that it begins with the letter Q. But we'll get to that soon.
I did it. It's exactly the same thing once again. P doesn't depend on x, so this vanishes. This becomes 1. So what we're left with is minus h over x, which means that once again, we know that this is the Hamilton equation, the second one. This information suffices. So what we see is the dynamics of the position and canonical momentum are described by the Poisson brackets. So not only do these Poisson brackets actually, yes, this is exactly how we define them. They describe the dynamics of your variables that doesn't explicitly depend on t.
Okay, so
this is good. It's very symmetric.
Yeah, in this case, it's a bit difficult to see, but this is effectively these Hamilton equations from before. As you can see, in this case, you have a partial of Hamilton in relation to a partial p is equal to q dot, and then reversed with a minus p. Our Hamilton equations right here. And then if we go down, this is the same exact thing, except with fish. And, well, unfortunately, French. Does that connection, because the connection should be very clear in this case. This is effectively, well, I don't want to say notation change, but it is the same exact equality. Okay, for a second I thought Mashri was saying that no, it isn't clear, but they're just complaining about the French. So I think we're good. I think we're fine.
All right, let's.
Any more brackets we could do, Remko?
Let's push our luck a tiny bit. So right now we defined Poisson bracket of a function, always with respect to the Hamiltonian. But we could just keep it more general. We could the Poisson brackets are generalized, but we could even generalize the Poisson brackets. I don't think they have a name. They probably are also called Poisson brackets. But we could just consider two arbitrary functions, and this is just literally defined as the first one with respect to x, second one with respect to momentum, and then we just rotate it around. This is the definition, I think. Yes. Okay, so with this generalization, we could also consider quantities like x and p, like the Poisson bracket of x and p. And I hope for some people, some bells are starting to ring. But for now, let's just write it out. I promise I won't be writing too many of those anymore.
You are getting much faster at them.
Yeah, I'm also getting more irreadable, probably. This one vanishes. This one also vanishes for the same reasons as before. And this one is 1, this one is 1. So what we get is this just equals 1. All right, let's consider, for example, this one. Well, we can just argue this one. We know that there's 2 x's, which means if both of these terms are going to be having an x with respect to a derivative of x with respect to p is going to vanish. So for that reason, this is just going to vanish. And the same exact reasoning holds for this one, for the Poisson bracket of 2 momenta. Now, we could, of course, generalize this for the many particles. So I'm just going to write that down here. It's the same definition as we had before. But we could also now consider, for many particles, the Poisson brackets. So what if we, for example, consider 2 different positions, the positions of 2 different particles? Well, you can just work this out. You will find that when you always get derivatives with respect to momentum. So this is just also going to be 0. And the same holds for the Poisson bracket of 2 momenta of different particles. So perhaps we might try our luck with this one. The position of particle I with the momentum of particle J. Now, since we are dealing, I'm going to argue this, but you can work it out. Since all of these Poisson brackets have like the terms, the product of the terms both have an index I. So both this X has an index I, this P has an index I. This term is going to vanish unless I and J are equal. Because the partial derivative of a position, I should probably just write this down. The partial derivative of a particle at position I to the position at index J, this is going to be 1 only if I equals J, and otherwise it's going to be 0, because the positions of different particles are independent from each other, and the same holds for momentum. So in that case, this is also going to be 1 and 0 only if I equals J, and this is if I doesn't equal J. Does that make sense?
And in the meantime, as everyone answers that question, I also wanted to say that Alex said F and G is the general fish bracket, and XP is sometimes called the canonical fish bracket.
Yes, that is correct.
Just as a...
Yes, they are called the canonical brackets, but this is a term we mostly use in
also,
quantum.
Timon still seems to be stuck on the partial derivatives from before. I think just like last time we had this kind of problem with the Lagrangian, with the generalized coordinate and the graph of the Lagrangian, and I think this might be also one of the things that we leave for the video, with the more proper gears explanation, with the more concrete examples, the Poisson brackets. I think then maybe it will stick. Because so far, I think maybe we should have a brief look back at what we've achieved. I think it's a pretty good spot, don't you? Before the next chapter, to have a brief look back at what we achieved exactly and what we have going on.
All right. So what we did so far is, from the last stream, we knew our Lagrangian formalism. Using this Lagrangian formalism, we defined a momentum in which we constructed a Hamiltonian that depends on the position and this canonical momentum. we then saw that in order to we can like use this Hamiltonian as long as we well have we can like it's equivalent to Lagrangian and Newtonian formalism. So there is no new information. There is no less information.
Still covariance still works.
Yeah.
For many
So
particles, we have the exact same thing. We know that they are additive. We know that both Lagrangian and Hamiltonian have that property. Then from asking the question of how does it change over time, we did see that energy stays conserved, which exciting fact, which we all celebrated at the time accordingly.
I had my whiskey.
So did I. That's why I wasn't talking. Don't worry.
Yes, and then we used the same reasoning to define the Poisson brackets. And using these Poisson brackets, we found some interesting relations between x and p, and we found that we can write the Hamilton equations very symmetrically in terms of these Poisson brackets.
Yeah, so this is everything that happened so far.
Are you guys still with us?
I think at least most people appear to be, because listen, now is the time. Everything you've seen so far, that was just an appetizer. That was the beginning. I know, I am fully aware that it takes up half the board. Don't worry about it. Don't think about it too hard. But it was just an appetizer. That was just to get you thinking. That was just there because this is mathematics. But now it's time to note down an equation which might matter a bit more. Remko, would you do the honors?
Yes, I will. But first, jokes aside, we might need a second board at this rate.
Yeah,
but yes, at long last, we have come to the climax, or the culmination of the entire show that we are giving. So let's just say that we have two general observables. These observables just means something you can measure. So in this case, it could be a position, it could be momentum, it could be energy, it could be angular momentum, it could be just anything that you can measure. What we are going to do is we can consider the Poisson brackets of these two. Let me just write down these are observables. And what Dirac did sometime in the past is he said that, okay, we have this Poisson bracket. What we are going to do is these are classical observables in a classical system. But we can make this quantum. We can make these quantum observables in a quantum system. And the way you do this is you take your Poisson bracket, you add a prefactor of minus I, complex I, h bar, divided by h bar being Planck's reduced constant, a very small value, and we have the same observables, but we put little hats on them.
It is the time.
And specifically, this bracket, this commutator as it's called, is defined. So this is a definition, is defined as the difference between them. The difference in the order of operation. So what we did is we took the observables, we promote them to operators, and we defined a commutator because apparently operators, or at least in most cases, the operators do not commute. In case of normal numbers, these two would be exactly the same. This would be 0. So what is happening here? What does this all mean? Before we get into that answer, one tiny
an example, I suppose.
Yes, one tiny example to show this a little bit better. We just saw that if we have the Poisson bracket of position and momentum, this is equal to 1. Well, we can use this rule to make it quantum mechanical. And we see that this Poisson bracket becomes the minus I over h bar of the commutator of x position operator and momentum operator. And this equals 1, which means that your quantum mechanical commutator equals I times h bar. And of course, remember that this is, well, the first term is the difference in the order of the operators. Now, as a very fun fact, this is Heisenberg's uncertainty principle. It's literally this. You can ask me questions in my Discord channel if you want. I guess this is the shameless self-promotion you wanted to make it.
Yeah, it's about time that one happened.
So
because I mean, how could it be? How could it be?
There is a lot to unpack here. So the first obvious question you might want to ask, what on earth is an operator? And the second question you might ask, well, if operators are matrices, what the hell do they act on? A follow-up question might be, well, if these operators that are matrices act on so-called vectors, what do these vectors represent? And you could just keep asking questions, but in the end, it's all about vectors. It's all about vector spaces.
And so as such, we will completely omit everything we've learned so far and take a wildly different turn to talk about something completely different, because right now it is time, after quite a fair bit while, I would say, to get back into the land of vectors and vector spaces. It's been a while since we've been here. Now don't worry, or do worry, depending on what you prefer, because in this case we would like some variety. So we won't focus so much on the equations. We will focus more on what certain things mean. So let's start simple. We have a cube, all right? Once again, relatable. We all love cubes and we all know cubes. Now let's say that we would like to represent the color of the cube, or even better, we'd like to assign it the color, because right now the cube is pitch black. And that's not great. What's the point of having a pitch black cube? It's boring. Let's give it some color. How are we gonna give it this color? Well, we mostly have 3 options. In almost all modern technology, we have 3. Usually, we can give it some kind of red value, we can give it some kind of green value, and we can give it some kind of blue value. Red, green, and blue. Why red, green, and blue? Well, it's because if we give it some red value and green at the same time, we can achieve yellow. If we get some green value and blue value, we can achieve teal. The same way, if we get red and blue, we get purple. I don't think I need to explain that much there. This is just colors. We're all familiar with colors. But now, let's make this a bit more concrete. Let's assign these numbers. So right here, we'll have the numbers. The numbers that represent our redness, our greenness, and our blueness. And so far as I move this arrow around, you can see that the color changes. Is everything clear so far? Because I'll be brutally honest with you. In this explanation, every single portion will be simple. It will be trivial. It will be something that my cat could do back before it went into the vat of acid. It's honestly simple, but there will be a lot of simple things, so they might get overwhelming after a while. Just let me know if that happens. I will try to go as slow as possible. Okay, so far I do believe that it's pretty simple. That's something everyone can understand. Now let's complicate it a bit, because what actually is our vector? Well, I am representing it as an arrow that points somewhere in space, but it is useful to keep in mind that it is actually these 3 underlying values. Or more importantly, it is these 3 underlying values that multiply basis vectors. So in this case, we have the basis vector of redness, of greenness, and of blueness. Now, I know it might not mean much, but if I add this to the mix, then you can probably see it better. If I move it on the x-axis, we are making the cube more or less red. If I move it on the y-axis, we are making the cube more or less green. If I move it on the z-axis, we are making the cube more or less blue. This is once again all simple stuff. I am just effectively moving the same exact arrow over and over and over again. That's in our typical RGB system. That's what it stands for, red, green, and blue. So in our RGB system, if we pick some kind of value, let's say, let's just say we would like something nice like purple. Why not? Wait, what if you go into the negatives, your RGB setup? What do you mean, what if I go into the negatives? What do you mean? I can just... In this case, what we're going to have is we're going to have red, green, and red, blue, and negative green. What is so confusing over there, Ash? That's simple. But without any tomfoolery, let's try to achieve purple. So for purple, we would like something like 1, 0, 1. There we go. This is exactly same mix of red and blue. We got purple, violet, magenta, pink, whatever you want to call it. It's in that section. But now let's ask a question, because what you might have noticed is that just like I'm moving our main color arrow, all of these additional color arrows, the basis vectors as they are called, are also arrows, right? So in this case, what we are doing is we are taking our values, we are multiplying each one of them by the color, and then we add them all together to get our color. This is the red, green, and blue system. By now, let's ask the question of, what if instead of the red, green, blue system, we would use red, green, teal? How could we do that? Well, that's simple. All we need to do is just move our blue arrow into the territory of teal. And now, our color changes. Instead of being purple as it was before, it is now white. Why is that? Well, if you pardon me some very brief calculations, that is because, and let's just simplify our numbers as well, just to make this a bit easier for us, just 1 and 1. That is because, in this case, what we are doing is we are multiplying 1 times 1, 0, 0, plus 0 times 0, 1, 0, plus 1 times 0, 1, 1. And so what we get is this disappears, which means we get 1, 0, 0 plus 0, 1, 1, which means we get 1, 1, 1, 3 ones, which means white. There we go. And the crucial thing to keep in mind here is that we can actually move these basis vectors whichever way we want. I can actually mess it up completely. I'm even putting the blue arrow, blue in quotes because it's the first base vector, I'm even putting into negatives because hey, who's gonna stop me? So now we can just put them whatever way we want, something really confusing, some really wacky colors that human brains were not meant to perceive. And now we can see that if we move our arrow on the x-axis, we basically increase how much of the first basis vector we add. On the y-axis, we increase the second one. And on the z-axis, we increase the third one. And as such, what we get is a new vector. Now, that's what I was talking about. As I mentioned, it's a lot of simple things, but there are so many of them, they may be overwhelming. And in this case, if I am not mistaken, there are 8 arrows at play. That is a lot. So, are we all clear on what has happened? One of the craziest lectures I've ever seen. Yeah, we did get a bit off topic, I suppose. Yep, alright. Glad we are all clear, because that is just the beginning. That's because if I reset everything, there we go, everything is reset, and in this case, what we get is just our usual red arrow, green arrow, and blue arrow. Let's, instead of doing red, green, and blue, just boring, let's change them up to something wacky. Now, this is a completely viable system. Don't question just how far into the negatives all the arrows are going. We are dealing with negative colors. We are here to solve physics and we can't let silly things get in our way. But there is a reason why I have picked this very specific basis, or as it's otherwise called, matrix. And that reason is because if right now we take our vector and if we set it to something like, just off the top of my head, 2, -3, and -1. something interesting happens. It's a bit difficult to see, I will grant you that, because it's honestly horrible with negative colors, but unfortunately, well, to break the fourth wall a bit, we just couldn't find a better eigenvector. It is a bit difficult to see, but what happens here is that our original vector, which is this segment of the line, just gets extended. So you can think of it as this very specific set of basis vectors, instead of changing our color, amplifies it. So our cube remains the same color, but the difference is this time the color becomes more pronounced, becomes stronger. And this right here is precisely the eigen, because that's what eigen is. It effectively means that if you have a vector, if you transform it using a matrix, and you get a vector that basically points in the same direction. More properly noted down, it would be something like the matrix that we apply onto our vector would be equal to the same exact vector, except with a different magnitude. This is the eigen of our vector. So, no questions whatsoever, really. You all mean to tell me that this entire explanation, and you've just felt fine through it? That there is nothing that confused you?
I suppose we have a smart audience.
I think we do. I mean, they've seemed to... We really over-prepared, haven't we? I do believe...
We do have a smart audience.
We do have a very smart audience. We have over-prepared like crazy. Or maybe we have smart teachers. Oh, stop you flirt. Well... well then, just as a brief recap, what's happening here is that we have our original vector. We have the matrix that we transform it by, and what we do is we take our first term, so we have x, we have the y, we have the z, and we multiply the x by this, we multiply the y by this, we multiply the z by this, and if we add them all together, what we get is this vector right here. This is the before, this is the after. And there are certain matrices for which the vector doesn't have to move around. It does also depend on the vector itself, not only on the matrix. So if I move this, then you can see that our resulting arrow no longer aligns with our vector. But if I get it back there, then it does align. And since I can stop until since picture and composition of functions based, but I suppose that's outside the scope of this video. That would be an overqualification, yes, Ash. That would be way too much. So, this is the thing I want you to keep in the back of your head. That's very important. When you see an equation, just hypothetically in the wild, an equation which transforms a vector, and in return you get the same exact vector multiplied by a scalar, that is the eigen. I'm just mentioning it because matrices are something we're all familiar with, and eigens get referenced a bit less. That's the only reason why I'm effectively mentioning it. And so with that all in mind, we have our linear algebra, but crucially, one thing you might have noticed is that the color becomes irrelevant. I mean, yeah, we started the color motivated the whole thing, but at the end, we don't actually care about the color. We can deal with the numbers on their own. So that begs the question, could there be other things we could describe using vectors? Remko, do you have an idea for one?
What a smart question. Yes, we can describe the entire universe with this.
Yeah.
But first, I have made a small overview of the linear algebra that MAKiNG just explained, and the relation to quantum mechanics with application of the color, the cube. So in linear algebra, MAKiNG just showed a vector. It's just an arrow pointing somewhere. In quantum mechanics, we refer to these as states. So when I say state, when you see a state, or even a wave function technically, what we mean is a vector in linear algebra terms. And for the cube, it was a three-dimensional vector, a three-dimensional array. Then another important notion is that we have a basis. We could decompose this vector into its basis vectors. In linear algebra, this is very straightforward. It's similar in quantum mechanics, except the notation might differ slightly. We could, it's essentially because there is two ways to describe states. We could just use psi, but we're also very fond of our Dirac notation, the bracket notation, where we describe states using this bracket. So when we use this bracket, your basis decomposition will be sort of similar. You will write your basis vectors also in these cats, and usually you use the numbers 1, 2, or 3. This might seem very reminiscent of qubits, and in fact it does. But that's not for this stream, unfortunately. Well, we saw that you could transform your basis, and this is done using a matrix in linear algebra. But in quantum mechanics, such a matrix is called an operator. These are exactly the things we saw before. They have a little hat on them, just to make it cool. And in the Color cube, this is just a 3 times 3-dimensional matrix. Then last thing, eigenvalues. So let me also quickly recap that from a physics perspective. Usually we are given a matrix. So we start with a matrix and we want to know vectors that scale under this matrix. So they don't get into another direction, they just scale. So we start with the matrix, we want to find eigenvalues, which is in this case the lambda, the number, and we want to find the eigenvectors. So these vectors are usually not given, we have to calculate them. In quantum mechanics language, this implies that we act with an operator on a state. And what we get is we get the same state back, but scaled. And this is usually called an eigenstate instead of an eigenvector. And if we want to write this in bracket notation, the way we usually do it, or the way we often do it, is if we have an operator which acts on a state. Usually we use the same notation. So in this case, m, or lowercase m. And what we then get, if it is an eigenvalue and an eigenfunction, or eigenstate, then we get m back. This is a scalar. And we get the same state back. This is just some notation. It's just... There's just a one-to-one correspondence between linear algebra and quantum mechanics. It's just physicists try to, I suppose, be more independent of mathematics and use some new definitions. And in the Color cube, we just saw this as a matrix acting on a vector, and we get the same vector back, but with a little constant in front of there. So we just scale them. So let's apply this. As I said, we're going to apply it to the universe. But first, let's make a new universe. So making a universe is going to be the next topic.
If someone new joined in right now into the live stream, this is the sort of thing we do kind of on a daily basis. You need to get used to it.
Yeah, this is physics. But let's, for now, make it slightly easier. We have a universe with 3 points. So we consider one particle in these 3 points, which means that the particle can only be at one of these 3 points. What we are interested in, or what we want to explain / describe, is the position operator. What does it do? What does it mean? First of all, we have a system. The system is just the entire universe. We have several states in which the system can be. For example, the particle can be in the first position, or the particle can be in the second position, or the particle can be in the third position, of course. What we do is, these are just the states of the system. So we're going to call them state 1. This means, if we see this means particle is in position 1. For the second one, this means particle is in position 2. And same holds for the third one, obviously. Now, okay, so we have a state. We know that there is a correspondence with linear algebra, So what we can do is we can write it as a vector. And we can write the second one also as a vector. The main important thing is that you don't choose the same vector, or preferably you also don't want to use a scalar multiple of the same vector. And when I say preferably, you're not allowed to use a scalar multiple of a vector. So now we want to know how the position operator acts on these states. And in linear algebra, this means we have a vector acting on this state. But we want to know all the possible eigenvalues of these position operator. So what we're looking for is operator, for example, for the first state. We want to act with our operator on the first state. And what we want is we want this to tell us that the particle is in the first state. So what we want is we want a number 1 here. Similarly, for the second one, if the position operator acts on the second state, we want this to tell us that the particle is in the second state. So we want this number 2, because it might be a good point to mention here that eigenvalues, so the ones in front of the vectors, those are the things we can measure. So for example, if you're in the lab, you're measuring energy, or if you're measuring momentum, if you measure such a momentum, it will be an eigenvalue that will be in front of the vector. That's why we're so interested in these eigenvalues. And we can do the same for the third one. And we should obviously have the number 3 here. So in this case, the position operator is just measuring where the particle is. But we can nicely do this in the linear algebra framework, where our operator now is a matrix, 3 by 3-dimensional matrix. And we know what our states are. So we have a 3-dimensional matrix. We don't know the values of this matrix yet. We just know that if it acts on 1, which is the first state, we should get an eigenvalue of 1. Now, this 1 only affects the first row, or the first column actually. So, no, it does affect the first row, I mean, this. So we could just make it very easy for ourselves. What we could do is, if we fill in 100, then we know that this equation always holds. And similarly, we can look at the second one. We now know the first row, and the second one should give us number 2. Because this is the eigenvalue of the second equation, this one. So once again, we can just look at the row, because this one this one is 0. The first one is 0, the second one is 0. This only acts on the second row. So once again, we could just make it very easy for ourselves and just fill this one in. But now there needs to be a 2, because we need to get this vector 2 here. And similarly, we can do it for the third one. And what we see with the same line of reasoning, we see that we have to fill in a 3 here, because our eigenvalue needs to be 3. Yeah, my bad. Hey.
It's all fine. Yeah, but the crucial thing to remember in this case, something that might confuse some people, and it's just very important to point out, I do believe, just in case, is that in this case, we are talking about position. We are talking about position in the universe. And yes, we are describing our position with 3 vectors. But very, very, very importantly, these vectors don't describe the position as in the x-coordinate, the y-coordinate, and the z-coordinate. They are just vectors. And in this case, we cannot have a position like 2, 7, 1. That doesn't exist. In this case, we only have 3 positions in our entire universe. Our universe has discrete positions. It's a bit wacky to get your head around, but I think it would help with, I suppose, an additional point. We don't need to draw it out exactly, but just mention.
Yes, these 3 vectors are in a arbitrary vector space, three-dimensional, but they do not coincide with x, y, z. The main thing now is we found we had like our operator, and we found a matrix expression for our position operator. And this, I'm just gonna call an equality sign here because they are the same way of describing the same thing. What this position operator tells us is if we have an arbitrary state. So now I'm not going to define in which point the particle is, it's just arbitrary. If we act with the position operator, it will just give us one of the states. So it will be just, let me just call it n, and the same state back, where this n is going to be either 1, 2, or 3, depending on where this psi is in. So psi is the particle, it's in either 1, 2, or 3, we haven't specified. Once we act with this position operator, we will know in which one it is, because this will tell us in which one it is. Is that clear? Does that make sense?
I think it is. Two things. First of all, Mashrit, if you're genuinely asking about the Hilbert space, I just want you to know that unlike most mathematical topics, Hilbert space is one of the only things, if not the only thing, that I do have a full video dedicated to. The only mathematical thing. Second of all, hey, quick advice, you never really explained matrix implication. I mean, I understand it because we did that. But I feel like it could have been something you dive deeper into. Timon, as much as I appreciate you giving me quick advice, have you given any thought that maybe there is a reason why I haven't explained matrix multiplication? I would really appreciate that if you didn't backseat me. It bothers me. And then next, make a video on it. Oh, thank you, Ren. Thank you so much, Ren. Now, does anyone have any questions about this specific thing, the position, in this case, discrete position of the universe? Because Ren was also speeding up us along to skip the linear algebra and get to the fun stuff. So I suppose we might as well just skip over the 4 and just go to... You know what? We did 3. Listen, we did 3. We did 4.
I'm not skipping. I'm not skipping.
I don't know. What I'm saying is that we did 3. We did 4. Oh, the next logical thing.
We did 4?
I mean, the 4 follows a pattern.
Yes.
Unless you want to add something to 4.
The only thing I'm going to add here is if we have 4 points in our universe, we hijacked a neighboring universe, for example, then we now have 4-dimensional vectors describing this. I guess that could be very useful to point out. And with the exact line of reasoning, what we find is that our position operator will now be a 4-dimensional, still diagonal matrix, where you just... Well, the pattern is evident.
Yes, so...
And once again, if you just act on an arbitrary particle, you don't know which it is, you will get your same n, but now your n is running from 1 to 34. And it just tells you in which of the 4 it is.
Could you please differentiate between matrices and vectors here? Matrices are the ones that are a square. Vectors are the ones that are a line. That is the difference. And I suppose it could be even... If you are talking about characters on their own, matrices have hats, whilst vectors have, well, cats. And scalars have nothing, because, unfortunately... Because they don't need anything, actually. They're good on their own. They already appreciate it. Now, in this case, we have our universe with 3 possible positions. We have our universe with 4 possible positions. The next logical step is obviously infinitely many, because what else to add? So, I mean, this is ridiculous, remko, like 3,
No,
4.
I'm going to write all infinity possible.
No, but this is ridiculous. Like what with infinite? What are we gonna have? Infinite vectors?
Yeah,
Oh,
is that a
well,
problem?
I'll be damned.
The idea is the same. You, well, technically you are considering n possible points, and you just send n off to infinity. So what you get is you get vectors that are mathematically infinite, where once again you can do the exact same trick. You just every point in your universe you just represent by a unit vector with a one somewhere, as long as there's no 2 points with the same one at the same position, etc. You can once again find your position operator, and what you find is this one is also infinite. So
Yeah, that is a lot of points then.
it is a lot of points, and even though it is infinitely many positions, the pattern is so easy that it just keeps going. That's the nice thing about this. You just there's like we went from 4 to infinity many, but nothing really
The
changed.
pattern is, I believe, clear. But there is still one question. There's this one tiny snag in this case, because these are still discrete positions, aren't they? Still points.
Yes.
Like,
Perhaps
and like, you know what? Infinite vectors, that I can, let's just say I can hypothetically stomach that, but what if instead of infinite amount of discrete points like that, we have a continuous infinite line?
Well, would you look at that? I just drew it. In this case, let's just pick one point of this line. We call it the state x, because it could be 1, it could be 2, it could be anything, just somewhere on this line. Now we can do the same exact trick. We can define the position operator. We can let it act on the state, and what it tells us exactly where the state is on the number line. Of course, as an eigenvalue. So with these 4 panels, what we showed is that your position operator, when acting on a position state, these are special states, but in this case, just possible positions of the particle, for example, you get your exact position on that number line back. There is a small disclaimer. This step of going from finite to infinite to uncountable is purely for illustration, and it might be mathematically
yes, which is
not that defined.
We want to protect ourselves against the mathematicians who will dissect this, and, well, they will, in fact, find out where we live. So this is just meant to be a nice little rectangle, in which case you can see 3 to 4 to countable infinity to uncountable infinity, the way things always go in life. However, quick question though, Remko, because this is position, right?
Mm-hmm.
But from earlier on, I vaguely remember that we were not only dealing with position, we were also dealing with another independent kind of coordinate, right?
Yes, and you are so right on that. We have a Hamiltonian. That's what we started with. We have a Hamiltonian, which is a function of position, but we now have explained the position operator for, but it also depends on momentum. Now, with the same line of reasoning, what we could do is we could have the momentum operator act on a set of momentum eigenvalues, and this gives us the exact momentum. So once again, you could consider this as a line of all the possible momentums. In this case, it's not a line in space, but it's like a hypothetical line. Where acting with the position operator, you just get with the momentum operator, you just get your momentum back. There is a problem with this. First of all, I indicatively wrote this as function of p. Whereas if I had to write this one, I would write it as function of x. Because the problem here is that x and p do not commute, as in their commutator is not 0. And we saw this because it is I h bar, which means that when our Hamiltonian is a function of p and x, it doesn't make sense to talk about two different states. Because these two states, this state and this state, they are not the same state, because these are the eigenstates for momentum, these are the eigenstates for position. They are not the same, they don't even have to be the same. In fact, they are related through a Fourier transform, but that is not relevant for our discussion now. So what we want to argue is, actually what we're more interested in is how the momentum acts on position states. An equivalent way of thinking about this is how the position act on momentum states, but we just have to choose one of them, and we'll choose this one. Because it's more comprehensible to understand position states. It's just somewhere in space. Or technically, it's the state of a particle being somewhere in space. Well, there is fortunately a nice argument to show what this should be, or how the momentum operator should act on position states. What we do is, in this framework of having an infinite amount of a universe with the infinite amount of points, the last example that we did, we are going to think of one such a state at position x. And then we're also going to think of the same state, but slightly to the right. So if we have our number line, our x is here, our other position that is like basically touching. It's like the same, it's infinitesimal distance to the right. This should be a plus, obviously. But we just want to see how these two relate. In other words, we want to write this as a function, as an expression which we can work with. Before I continue with this, let me first tell you, hopefully there's no mathematicians in chat, but let me first quickly tell you two reasons why theoretical physics is fundamentally different and better than mathematics. First reason, of course, is we sometimes go outside, look around on how the universe is working, so we can match our equations to that. Second reason is much more important, I would say. We, as physicists, have Taylor expansions, and we are not afraid to use them.
Did someone say Taylor expansions? Oh, never mind.
Yes.
I'm stopping this then. Well, I'm sitting down for that.
It's all we need in physics. So let's Taylor expand this, and I will, for the first time ever on stream, so this is like, wow, you guys are blessed that you can
Cherry, this is
just
important.
witness this.
This is important. I cannot stress it.
Yes, so what we do is we have the second, we are in the second position, our wave function of the particle in the second position. We can write this as the wave function at the first position, but with a small correction, specifically this correction. And we can write this as an infinite polynomial in this case, epsilon. So let's do that. But first, this should be a minus. My epsilon. And then the derivative of the wave function in this case with respect to x. And then, what? My line is not going away. Well,
No,
malfunction.
Technical
The document
difficulties.
was not ready for Taylor expansions. Yeah, but the problem is the moment I touch down my mouse, it makes a new line. Oh, perfect.
There we go. All right, fixed.
All right. Let's go back to this. Taylor expansions is so we just first consider the first derivative. We would then consider second derivative, etc., etc. This is just going to be a polynomial on order epsilon. The thing is, we're going to send epsilon to 0. So all we really care about is the first order, because epsilon squared is going faster to 0 than epsilon. Now, the first question, or the first term, I mean, this term represents our original position. But we then shifted a tiny bit to x plus epsilon. The second term represents this shift, but a change in position is governed by velocity, or in this case, momentum as our independent coordinate. So what this means is that this is going to be our... like if we would have to make an analogy with classical mechanics, then this would be our normal position, this would be our velocity, and this would be our time. And yeah, that would be a plus here, and this would be our new position. So what this means is we're now in quantum, so we don't have velocity, we have momentum. This means that our momentum operator acting on our wave function, I guess there should be a cat here. Acting on our wave function is going to be the derivative of this wave function. And we could scale this with a constant. We don't know this constant. It depends on how epsilon depends on time in the analogy. But it turns out that using the commutative relation, the one we found, IH bar, you can show that this constant is... well, you need to be a tiny bit careful because if this is a derivative, this momentum, you will get a chain rule when acting on a state. So you need to act on the state. If you have, you can work it out yourself. If you have any questions, feel free to come to the Discord. Hint, hint. What you will get is that your momentum operator equals minus I, complex number, h bar, Planck's constant, the derivative of with respect to x. And now we really see the nature of operators, because you can represent this as a matrix, obviously, but this term, this momentum term, doesn't mean anything on its own. It needs a state to act on, because this is a bare derivative. You need something to act this derivative on, something that gives it a value. And that's the whole point of operators. They can't be alone. They need to be accompanied by a state or a vector. Is there any questions on that?
It doesn't appear like there is. I feel like everyone... That was a tough rule as well. I'm impressed everyone understood that as well. I think there's nothing... I think everything is fine. So now effectively what we've got, just to make sure we're on the same page, is basically how a momentum operator acts on a state, correct? Because we figured out the momentum operator.
Specifically on the position state, on a position eigenstate.
Oh, okay. That's good.
Yeah, okay, so we know now what our momentum operator does, which means we know both our momentum and position operator, which means we can now think of what our Hamiltonian on a state does, and this is going to be a position eigenstate. So in classical mechanics, this represents the total energy of the system. The Hamiltonian is total energy. So in quantum mechanics, the system is represented by states, by vectors. So we need to somehow find the energy of a state. So we want something of the form energy times your state. But the problem with this is we need to find a way to relate the left-hand side with the right-hand side.
Actually, hold on, because I don't know if I'm getting off my horse here. I don't know if I'm semi far ahead, but that does, if I had to guess, it does kind of look like the eigenvectors from before, where on the left you have a vector transformed by a matrix, on the right you get the eigenvector. That's kind of what it looks like.
Wait, so you're saying that this is inequality and we need to solve if we want to solve the quantum system, we need to find the eigenvalues of the Hamiltonian when acting on states?
I suppose I am saying that you need to find the eigenvalues of a Hamiltonian to figure out the allowed
That is insanely smart. We should try this. We should immediately try this for the free particle.
Brilliant idea.
Let's just go for it. Let's see if it works out. All right. So we have in classical mechanics, our Hamiltonian is going to be p squared over 2m. We saw this before. So when we upgrade to quantum mechanics, this effectively means that all the observables, in this case Hamiltonian and momentum, become operators. This is formally done through upgrading all the Poisson brackets in to Dirac commutator equations. But this is effectively what it comes down to. So when acting on a state, the Hamiltonian acting on a state is going to be p squared acting to m acting on the state, and we know that the momentum operator is the derivative. So what in this case what we get is we need to square it, so we get minus squared is just plus, I squared is -1, h bar squared is, funnily enough, just h bar squared. We still have the 2m, and we get the second derivative with respect to position of the function. And I'm not writing the bracket notation anymore. I'm just writing it as pure, like as psi, just wave functions, for the sake of clarity. What this means is we want to find the eigenvalues of this, which means we want to find the energy and the psi such that this equation holds. Well, we can just simply rewrite this, where we find the second derivative of the wave function with respect to x is minus 2me divided by h bar psi. So first of all, notice how this taking the derivative twice gives you a minus sign. So of course this is going to be a sine or a cosine or an exponential. But there is one slight difference with what we did in classical mechanics. We are now, instead of solving with respect to time, we're solving with respect to x, which means that your sine is going to be a function of x. When we want to consider time, what we effectively need to do is we need to solve the Schrödinger equation, and this gives us an extra factor of time, an exponential usually, and it's not that hard of a calculation, and it's not that insightful, so I'm not going to do it here. But this already shows us that the quantum free particle is more general than the classical free particle. In particular, we saw that all the Lagrangian, Hamiltonian, Newtonian formalism were the same for the free particle, but now we get to the quantum Hamiltonian formalism, we get something entirely new, something entirely difficult.
Yeah, and as fun as it is, we unfortunately didn't really have a budget to simulate it or render it in any way. We kind of blew all of that on creation of new universes. So how about another example, hey? Do you have anything in mind?
Yeah, this one is boring anyways. Who wants to see the simulation of that?
Yeah, anything.
I guess no one can guess which example is going to be the second example. And if you're still watching the stream, definitely watch for like 30 more minutes, because this is going to be the shit. This is going to be so glorious. First of all, we had our Hamiltonian in the classical mechanics of the harmonic oscillator. I have asked many times, I assume you guys know it by now. Hamiltonian is total energy, so p squared over 2m plus kx squared over 2. First of all, this was something we saw in the last live stream, where we found solutions where the k was going to be a function. We found solutions with a frequency which was going to be a function of k over m squared. This follows from just solving the equations. I'm going to, for convenience, I'm going to write the k. I'm just going to rewrite this in terms of this. And I'm going to use this mw squared for reasons which will come apparent later. The k is just not that useful of a constant. We would rather have something that depends on mass and frequency. So this is going to be... If you're not sure about this step, just go back to, well, after this stream, go back to the other stream and check that this was an equation we got. But this is going to be m omega squared x squared over 2. Now let's upgrade this to quantum. So we get Hamiltonian is going to be a operator. Our p is going to be an operator. Our x is going to be an operator. And, well, we just follow protocol. Let this Hamiltonian act on a position operator. I'm going to add the position dependence because now it becomes clear why we wanted position dependence. What this means is we got our expression. Let me just immediately fill in the p squared as we did before. By 2, and this all acts on the position state. Now what we know is we know how the x acts on the position state. What is, because we just get the eigenvalue of the position operator, and this is just the position at where the particle is. So we can just drop the head here. Is this clear? This should not be a dot. Effectively, in the left-hand equation, this is an operator that acts on this. In the right-hand equation, this is a real number multiplied by this vector. I guess if I want to write this specifically, we would have this expression. Just twice, because we have a square. Because we could just do this. Does this make sense?
No one seems to be questioning it.
Is there people left in chat?
I don't think anyone is in chat, which honestly, it's so upsetting how many people left for the most important part of the entire live stream.
They're missing out. It's okay.
Don't worry,
At least
I'm
we
going to
have
shame
stuff.
each and every single one of them in the video.
I mean, people have that life, I suppose. Let them live their life. So what we want to do is we want to find the eigenvalues of this Hamiltonian operator, which means this is a... Well, E is just a number now, so this becomes a differential equation. Minus I plus this differential equation in terms of x equals E. But this equation is very, very difficult to solve, which is a problem because we want it to be solved. Does that make sense?
I suppose, yes. I suppose it does.
Good. Let's continue. So what we are going to do instead is we are going to write it back in momentum form. To m, just because I want to showcase something, namely that apart from some constants, we have a sum of squares. The Hamiltonian is a sum of squares. I guess what I want to write here is the Hamiltonian. this is what we saw before. We have a square here, and we have a square here. And let me make this an operator again. So we're going to be a bit smart because we know some algebra with some of squares. But in this case, we are complex. So instead, we're going to be looking at this identity. So it's just a plus IB times a minus IB. And what this is the sum of these two squares. So that's good. But we also get like a factor where we now suppose that A and B are not commuting. So we can't like cancel this out. I suppose I should add little heads on here. Now, if we consider this for a position operator and momentum operator, then the nice thing that happens is we get these squares. These are the ones we want. And for now, I'm just ignoring the constant. We will get those back in a second. And this is going to be the commutator of, I guess it's P and X. So it's just the opposite than what we used to. And we know that this, in this case, it's a minus sign. It's a minus because it's opposite. And well, this is just a number in this case. It's not an operator anymore. So what we're going to do now is let's just take care of the constants and define the following two operators. Once again, this expression looks very complicated, but that's just because there is a lot of constants right there.
Constant, as always, especially with oscillation.
So this is our A operator. It's just the first term, the X plus IP. Our second operator is going to be a dagger. So this is a dagger. For reasons beyond the scope of today's stream. This is because this is the Hermitian operator of the first one. But let's just forget that if you don't know what that means. But this is going to be the other one. It's going to be minus. And what I will leave as... Oh, wait, using this... we almost at the end of the page. Using these two relations and the commutator relation of X and P, we can write our Hamiltonian in this form. So you have h bar times omega times the operator A dagger times A plus a half. And this half follows from the commutator that we just showed. That's the constant term. And now we are going to define this product of these two, of the A dagger times A, as the N operator. And this is called the number operator for reasons we will show in a second. So this looks complicated, but what we did is we had an algebraic expression. We didn't know how to solve it. Well, we do know how to solve it analytically, but it's like it's a mess. It's too difficult. It's like so many pages of writing it out. So instead, we just decided to be a bit smart, and we decided to notice that there is a sum of squares. We can write that as a product of two terms. And well, if you define these terms properly with the right constant placement, you get a very simple Hamiltonian. And there is also one more thing, which you can calculate yourself as well. And if you are stuck, you know where to find a Discord. Damn, the shameless self-promotion, really.
About time.
I plan to do one shameless self-promotion, but I did like 4 of them.
Don't worry, it was just 3. But about time. I support it.
Yeah, otherwise I'm not getting paid. So the commutator of A and A dagger, which is defined as the difference between the products, is going to be 1. This means that if you see an A and A dagger, you can swap them around. So if you want to change the order, you can swap them around, but you will get an extra cost. You will get a +1 factor. So we now want to see how this has helped us in solving, because we have just rewritten our Hamiltonian. We have not done anything with it yet. So what we're going to do is we're just going to find the eigenvalues of the number operator, this guy, and we're going to write this as this. So this is the number operator. This is the eigenvector. And this is the same eigenvector. There should be an equality sign here. And this is just a number. I write it in this way because it's like a very convenient way. There's a lot of n's, I know. But you'll see in a second why this is written this way. I'm also just already going to write this expression down. This is exactly the same expression, but we just shift n by 1. So if we want to find the eigenvalue of this one, we will get this. Does this make sense?
I do believe it does, just picking a different n.
You just replace all your n's with n minus 1. Because if n is an operator, if n is an eigenvalue of the n state, then n minus 1 will be an eigenvector of the n minus 1 state. Eigenvalue. All right, so in terms of this, your Hamiltonian becomes very, very easy. If you have the Hamiltonian acting on one of these eigenstates of your number operator, you will see this. This is just filling in. And this is going to be a small n now, because we explicitly act on our state. And what we want is we want to find the eigenvector of this in terms of your n state spaces. The problem now is we don't really know something about n yet. And we can try to think on what happens when we let n act on, for example, when we first, we have a state n, we first act with our a on this state, and we then act with our n. So we're just gonna see how the a operator, what it does with our state. And this, we can just write this in terms of definition. This is just the definition of the n operator. Then now we want to swap them around. That's why we introduced the cost of 1. So what we want to swap the first one with the second one. And what we then get is first the A and then the A dagger. But then we still have this cost of 1, which is now -1, because it's the opposite order. And the other ones, the A is still there. But what we now see is if we slightly rewrite this, we can pull the A in front. This is this A, but also this A. And right from this one. And then we open the brackets like this. Well, yes, so this A is now here. It's just multiplying out the bracket and then immediately bracketing again, but now in opposite order. And what we then see is that this term is once again the number operator. And we know how this acts on the number eigenstates. So this will just give us a vector n minus 1, small n, still acting on this. And if we rewrite this nicely, we get this. So why did we go through all this effort? What does this mean? Well, what we saw is if we act with our number operator on a state that has been acted on with our A operator, then we get the same operator. So this is in this case, an eigenvector, an eigenstate, but now we have a eigenvalue of n minus 1.
So what would happen if instead of A, we just add an A dagger?
That is a very good point. I will do that in a second. But first, look at the equation I wrote down before, like the n acting on n minus 1. This one? You have that one on screen?
Yep.
Perfect. What this means is that since we can only get the vector n minus 1 if our eigenvector is of the form n minus 1, and this is where it's slightly confusing because of the notation, but basically we can only get this eigenvalue n minus 1 when our vector is this n minus 1 state. So what this means is that our A dagger of n is of the form n minus 1. And usually, there could be a constant, a normalization constant we don't really care about right now. What this shows is that when acting with our A operator on n, it's going to give us a state that is in n minus 1. So effectively, it's lowering it's lowering the eigenstate. And for this reason, it's called a lowering or annihilation operator. And now, as Make it suggested, we could check the other thing. What happens when we first act with a dagger on an eigenstate? And if you do the same steps, the same analysis, you will see that this will be n plus 1 times the same thing. So a dagger n is once again an eigenvector of n with eigenvalue n plus 1, which means that a dagger acting on an eigenstate is going to be some constant once again times a higher eigenstate. So, and for this reason, it's called a raising or creation operator.
Or in other words, if we have some kind of state, we can figure out the next or the previous one using these two operators.
Yes.
So that is extremely, that is incredible in this case. That is a huge clue. But then still the question remains, we would need some kind of a starting point, wouldn't we? We would need some kind of state to start with from which we can go up or we can go down.
That is genius. Let's, for shits and giggles, consider what happens when we define, when our n equals 0. What we then get is A acting. I guess in this case the constants are slightly irrelevant. For our lowering operator, so annihilation operator, this constant is going to be the square root of n. For our this is just follows from you want your eigenstates to be normalized, otherwise they are not states, they're not quantum mechanically relevant, whatever. The whole I can help with this if there is any confusion, but not now. For the creation operator, the constant will be n plus 1. So when we consider n equals 0, we know this. This is going to be n, but this is going to be the square root of 0, 0. So this is just going to be the 0 state or the 0 vector, which means that, well, can we go lower? What if we try to go lower? Well, we have seen that this is just going to be 0, or well, the 0 state technically. So this is once again going to be the 0 state, which means that n equals 0 is the lowest we can go. Any lowering operator acting on this will still get us 0. So for this reason, the 0 state is called the vacuum state. It is the state where there is nothing in the system. Well, nothing is a big word, but if, for example, you're considering particles, then the vacuum state would be the configuration of the universe where there is no particles involved. And the moment you start acting with creation operators, you start adding particles. But we have now solved this system. There's two things. First of all, the n can only be an integer because you add 1 and it starts at 0. So what we could do now, finally, after all this long time, we could first of all consider the case of n equals 0. What we then saw is our E is going to be the Planck constant times omega, 0 plus a half, and this is just a half h bar omega. Same for n equals 1. In this case, it's going to be something. I'll just add like little subscripts here just to make sure they are not the same. It's going to be 3 over 2 omega, and we could do the same for
third one. Yeah, the pattern is clear in this case, that makes sense. But there's one curious thing that I've noticed there. And that is the lowest possible energy state. Despite being the lowest possible, it doesn't appear to have no energy.
Well, would you look at that? The vacuum has energy. Maybe this is the reason that we can have particle creation. Maybe the vacuum has energy. Maybe we can borrow energy from this vacuum to create a pair of particles and annihilate them again. Maybe this is where the Casimir force is coming from. The fact that two plates, when nothing even attracts, still push each other away because of particle creation within these plates.
So many hypotheticals. Wow.
Obviously, they're real. Wouldn't you believe that?
No way.
So, technically, well, you can solve for the wave functions as well here. I'm not going to do it, but I can visualize this. So if we have our lowest state, so this is the n equals 0 state, then the energy of the state is a half h bar omega. We can consider the next state, and this has this as 3 over 2 h bar omega. And once again, we can just keep climbing the tower. And the way you go from one state to the other state is using these creation and annihilation operators. So this just keeps going. So let's say we want to go from state 0 to state 1. We would have to act with a creation operator. So starting from the vacuum, you get to the first excited state, which is just n is 1, by adding a quantum or a quanta of h bar. So you could in fact see this as just adding one particle which has energy h bar omega. And if you want to go from the first excited state to the second excited state, you just keep doing the same. But you could also just, for example, consider going back. So if we start in the second state and we want to go to the first state, we would have to act with our annihilation operator or our lowering operator. And what this means is we just remove h bar energy. The particle just stops existing. Effectively, you just give your energy to the field again. That's a spoiler for later. So what we saw is we got a very important or a very difficult equation to solve, a differential equation, but we have made it so simple using these, ladder equations, ladder operations. We just acting with the raising and lowering operators, we just climb or we just descend. But we can reach any state with this. And that is very powerful.
That is an unbelievable thing. Just at this point, effectively means that we just have a number which gives us the energy state directly. From this, need I remind all, this.
I guess.
I think this will be a good time. Well, normally.
Is there? Yeah.
No, do go on.
I was asking if there's any questions.
Okay, then never mind. I sometimes forget that we are on the same wavelength. Because I was about to say that it would have normally been a good time to ask questions, but I do believe everyone watching at this point is asleep, unfortunately, because no one has said anything for a considerable length of time. Which is unfortunate, because this one...
Maybe they're all in awe.
Oh yeah, they're speechless. You know
They're
what,
speechless.
you're
They made
right,
them
they are
speechless.
probably just speechless. Everyone is probably just extremely speechless. Well, I suppose if no one is...
Yeah, we went from the Hamiltonian or the harmonic oscillator to a package of energy. So the Hamiltonian oscillator is just described in, we keep adding one quanta of energy to reach like higher excited levels. Damn, Caper. That's one way to answer.
Wait, Caper? Why am I not seeing Caper's message?
I guess it's not that much of a message.
Oh, I don't see it at all. Well, how? No! Oh, well then.
I guess it just shows up late for you, but thank you, Caper, for your donation to.
Oh, yeah,
charity.
that is true. Oh, I see.
All right. So, I guess
yeah, no,
if there
I think
is...
YouTube just glitched for me. I take it back. Yeah, technical difficulties as always. Caper, I will add your €5 to the website then. The entire time I thought no one was watching. I thought we were just... I honestly thought you were just doing it for me, Remko. If I'm to be completely honest with you.
It's a good thing we're making a video out of this to reiterate the most important parts of this.
Oh, don't worry.
For now, let's just give a brief summary of everything we've done. We started with the Lagrangian, we defined the Hamiltonian formalism, we found the Hamilton equations, which is basically the equivalent to the Lagrange, Euler-Lagrange equations. We just did it for two examples quite quickly. We saw that it is equivalent to Lagrangian and Newtonian formalism. We then upgraded to many particles, has some very nice properties. We then considered Poisson brackets to see how functions change, and this is related to Hamiltonian. And the main point of the stream came when we upgraded our Poisson brackets to commutators of operators. And this was a huge step we made, and it allowed us to write our Hamiltonian in terms of operators in a quantum system. We gave a brief review of the algebra, the quantum mechanics, how it relates to quantum mechanics. We even created some universes, our own universes, might I say. We showed how the position operator acts, how momentum operator acts as a derivative, how Hamiltonian x, how you need to find the eigenvalues of the Hamiltonian, the energies, to solve a system. And then we did the two examples. First, the boring one that we didn't really have budget for, and then the harmonic oscillator, where we found very curiously that we can describe we can describe the Hamiltonian oscillator or the harmonic oscillator in terms of raising and lowering operators, which are basically equivalent. It's a very powerful formalism with these creation and annihilation operators, because we will be able to describe all kinds of particles in fields, which is
I would like to
foreshadowing.
accent that fact that without, because it's honestly kind of easy to take them for granted, especially later on, next live stream, hint hint, nudge nudge. It's really easy to take these kinds of operators for granted, but I would like to accent without them what you would need to do in order to achieve the same result.
Yes. Yeah, using these creation operation particle operators, we can create the actual particles in actual fields, and especially if we combine different fields, we can describe all kinds of interactions like quantum scattering, electron decay, all the fun stuff that we are going to do in quantum field theory.
Timon does appear to have a question. If you go back to the part where we got the p operator from the psi x plus epsilon, I don't understand the step of the commutator. Where did that? Right here, right. So this. In the meantime, I'm gonna say Remko X is the collab that makes physics less daunting than the not so mediocre academia accidentally doing the opposite most of the time. We did try. Remko tried a lot. I'm gonna do the video. We collectively do spend a lot of time on these. It's a lot of effort. But yes. So I'm glad you appreciate it, Kaipe. I'm glad you're enjoying it. But back to the question, right?
Yeah, I will answer the question. The part with the commutator is not that relevant to the entire story of the momentum operator. The main point is that the momentum operator is a derivative, but it can still be some constant. And once we know how, we know the commutator between these. So if this is just I times h bar, and while acting on the state, it's going to be this. This is a given. So what we can do is we can just fill in our c, our constant. We can just fill in the p operator. So it will be this. There should be a psi here, x, but then now we have x times psi, and this needs to equal to I h bar psi. And what you can derive from this is that basically you get a product rule which will cancel this term, which will leave you with one term. And from that you can derive the constant. You can derive that this and this constant, you will find some equation which is exactly this equation. It might actually just be this. C might be equal to h bar. Yeah. With the minus sign. But you only use the commutator to find the constant. And it's one way of finding the constant. Technically, this is done by means of a translation operator, where this is technically the translation operator of T of epsilon, which is some very specific form. I think it was this form, or maybe the other way around. Regardless, it has some very specific form, and if you just match these two equations, you will find the constant as well. It's just one way of finding the constant. That is the big deal of the commutator relation there. It doesn't add any other value than finding the function, finding the constant. Okay.
Okay.
So
anything else? I don't.
Yeah,
At this
any
point, I
final
don't trust my
questions?
YouTube anymore. I don't know if no one is saying anything, or I don't know if my YouTube is glitching again.
Maybe Sunday evenings is the way.
It's, you see, that's the problem. It is a big mathematics trying to undermine us after they heard you talk about Taylor expansions.
It's the algorithm. They're onto us.
So,
So
that would be it for this show, I suppose, then.
Powerful formalism. We can do so much with it. We could even go to quantum field theory with this.
Wait.
There is one time problem.
Wait, hold on. Quantum field. Actually, you know what? That's a fair point. Wait, what is the problem? What is the problem to get to quantum field theory from here?
Well,